What is going on, everybody, and welcome back to part 3 of our deep learning with Python and Pytorch tutorials. In this tutorial, we are going to be actually building our neural network and at least really basically explaining how we pass data, and then in the next tutorial, we'll actually train the neural network. So in the previous tutorial, we actually got our data, kind of explained things like normalizing and balancing and stuff like that. And now we're going to actually build the model itself. So in order for us to do that, let me make a new cell here. And we're going to call this class, or actually we're going to make a couple new imports. So we want to import torch, torch.nn as nn, and then we're going to import torch.nn.functional as f. So the way I understand this is most things are kind of in both of these versions of PyTorch. Torch.nn is more of like your object-oriented programming, and then torch.nn.functional is more of just like functions. And in general, we're going to be writing object-oriented programming PyTorch, but there's going to be times where you actually just want to run a specific function. So you'll see what I mean, but in general, these two libraries are interchangeable. So if it exists in NN, it exists in functional, and so on. And just keep in mind that, like with functional, you have to always like pass parameters, whereas like with NN, it would just, you would initialize things, right? And so some things, to my knowledge, don't actually exist in both. But anyways, most code that I've seen ends up using both. In theory, I think you could write everything as a function in PyTorch, but I'm not sure why you would. But anyway, I'm not a PyTorch expert, but basically these two things are very, very similar, and depending on exactly what you're trying to build, you might use something from just NN or something from the functional. But anyways, carrying on. So now, we'll build our neural network. So we're going to say class capital N net. It is going to inherit from nn.module, and then we're going to say define init self, and we are going to first initialize nn.module. So we're going to say super init. And if you don't know what this does, basically all this does is like super corresponds to nn.module, and all this is doing is running the initialization for nn.module as well as whatever else we happen to put in it. So when you inherit like the methods and attributes, so long as they weren't set in init, I suppose. Anyways, you inherit at least the methods, and but the thing is, the initialization method is not run. So if you want the initialization method to run of your parent class that you're inheriting from, you run super init. If that's fuzzy to you for any reason, go to the text-based version of this tutorial. I show a couple of examples with classes and importing, or not importing, inheriting. So it should clear it up there. But if you have further questions, feel free to make a comment or ask in the Discord. So let me do, I guess, trying to decide what I think we'll just start defining layers. There's something else I want to talk about here in general, but first we'll define our layers. So in our init method, this is where we're going to just define, we're just going to define the fully connected layers to the neural network. And then in another method, we actually define how data passes through. So what I'm going to say is self.fc1. So FC stands for fully connected, and then the 1 is just our first fully connected layer. So we're going to say self.fullyconnected1 equals nn dot, and then we're going to say linear. And this is going to take, basically, you've got input and then output to each layer. So the input is quite literally our images. Now, I happen to know the images, when flattened, are 784, but you might not. So where does this number come from? And this is kind of one of my complaints with both TensorFlow and PyTorch docs, is that sometimes they like throw these numbers and it's like, whoa, where did that come from? And they like half explain, but then they miss certain things. So especially when we get to the convolutional neural network, we'll point that out again. But anyways, 784 is 28 times 28 because our images are 28 by 28 images. And we can't pass the image. Instead, we pass the flattened image. So you can think of pixels, they're like rows, right? So you've got rows of pixels. And when we flatten those, what we're doing is you got your first row and then your second row is down here. Well, we actually take that second row and we put it over here. So eventually all of the rows just make a flat row of pixels. So that's what we refer to generally as flatten. So the input will be a flattened 28 by 28. What's the output? Well, our target here is to make 3 layers of 64 neurons for our hidden layers. So the output will be 64. So for every fully connected layer, we're going to have input, and the input is whatever is coming into this layer. So in this case, the input is the actual input layer, which happens to be the flattened image. The output can be whatever we want. So we could say this if we wanted, but we're going with 64. So finally, the next thing is nn.linear. This just means fully connected. It's just a flat, simple. You might also, when we do a convolutional neural network, it'll be nn.conv and so on. So cool. I think I've described everything there. So now we're going to say pasta, pasta, and then we'll do one more pasta. So then we're going to say 2, 3, 4. So keep in mind, though, that certain things have changed when we go from image to actual code, because this is the extent of our input layer, right? And this number here is kind of the extent of our hidden layer. The hidden layers are almost in between these calls or something. But anyways, fully connected 2 takes in 64 because the previous layer outputs 64, so this one has to take in 64. But now what it outputs, we could pick anything we want. I'm going to go with 64 though. So that means layer 3 has to take in 64. Again, we could output anything we want. I'm going to go with 64 again. So this final layer 4 takes in 64, but we said this was a 3 by 64. So you got 64, 64, 64. And then this is our output layer. So I'm going to say 10. Where does 10 come from? We have 10 classes, right? We've got 0, 1, 2, 3, 4, all the way to 9. So this is our output layer only has 10 neurons. Cool. So that is our init method. It's done. We actually could define our network now. So we could say net equals capital N net, and then we can print net. Cool. So we get to see this because we get some special methods from module. So what might happen though if we forgot super init, right? So part of learning to work with any of the deep learning libraries is getting used to seeing some of the errors and working through them. So if we ran this, we would get the following: attribute error, cannot assign module before module.init call. This is not the most helpful error in the world. You would have no idea what the heck that means, but it means you forgot your super init. Now, normally it wouldn't be commented out, right? You wouldn't have even had that line there, so it wouldn't be totally obvious. Now, I'm sure if you Google this, you might find the answer, but yeah. So as I think about common errors that you might hit, I'll try to show them. But for the most part, you can Google them, or you can post a comment, or join the Discord and ask. Cool. So continuing along, so we've defined our layers, but what we don't have is any path for data to take through these layers. So a simple neural network is what's referred to as a feed-forward neural network. It means data passes in one direction. It just goes one side to the other side. Nothing fancy. So for feed forward, it's a lot of F words. For feed forward, we're going to say define forward, and I'm going to make some space here. And what we're going to say here is self, and then the input is X. So the input is the data, and this is the actual method that defines how the data will flow through our network. You know, we could have called these layers anything we wanted. We just said FC1234, but if we wanted, we could actually attempt, it would fail because this is 64, but we could attempt to actually start by passing data through fully connected 4. Again, it's not going to work because the size that fully connected 4 is expecting is a 28 by 28. So it wouldn't work out, but we could if we change this to be 28 by 28. But the order that we've defined these layers is irrelevant, just for the record. So how do we want data to pass through here? This is the cool thing about Pytorch, that if you're just starting out and you've never worked with any other library, is going to be probably lost on you. but you get to choose anything you want. So we're going to define something pretty simple. We're just going to say X as it passes through. We're going to say first X passes through fully connected 1. So we're going to say self.fc1 X. That's it. And then we're going to do the same thing. We're just going to say, hey, X is going to pass through all the layers, right? So we're going to say pop, pop, pop. And then we'll say 2, 3, 4. So X equals fully connected X. So it redefines X. And then we pass it again. And then we pass it again. And then we pass it again. In theory, you could embed like all this stuff. It would be like one really long line. It would be super ugly. But you could do it. And then return X. So in theory, I mean, this would work. This would run. You could pass data. It probably won't learn. Why won't it learn? Because data won't be scaled properly, most likely. Why won't it be scaled properly? We forgot our activation function. But you wouldn't... I don't think it would error, to be honest with you. I'm pretty sure we could run this and we could attempt to adjust weights and biases and stuff like that. But it's not going to work out well because we don't have an activation function. So what we're going to say instead is we're going to pass capital F dot ReLU, which stands for rectified linear. This is our activation function. So we're going to run literally an activation function over that entire layer. But just remember, this is part of the helperness of Pytorch. I've never seen anybody do it, but in theory, you could have, I think, different activation functions per neuron. I've never seen it done. I can't imagine why one would do that. But that's possible, especially if you made such a large... because I'm just getting way ahead of things. Never mind. Anyways, rectified linear is the activation function. If you forget what the activation function is, this is whether or not the neuron is firing, like the human brain, right? So, the neural networks kind of came from trying to model brains. The brain, however, as far as science knows, is really more of a stepper function. The neuron is either firing or it's not firing. In the case of most activation functions, it's not a stepper function, it's a sigmoid, so it's a range between 0 and 1. But regardless of what activation function it is, it keeps the outputs of these layers from just exploding into these like crazy numbers. It can still happen, especially when we go to like compute gradients and loss and stuff like that. These explosions can still occur. But we do everything we can to try to not have these magnificent explosions. So, and if that doesn't make sense to you, don't worry. We will continue ratcheting up and you'll soon learn about loss explosion. Okay, so we want to actually run this on every single layer. So in fact, I'm just going to copy and paste again. So post. And 2, 3. And actually, we don't want to run that on 4. We just actually want to pass the data. We'll just pass it just so everything's nice and explicit. So for these like 3 layers, and keep in mind the activation function kind of runs on this side, right? It doesn't run on the input data. So that's being run on this 64, this 64, this 64. But then on this 10, we're not actually running anything on those neurons yet. We don't want to run rectified linear here, because that's not the actual task. Again, the neural network doesn't really know anything about anything. So when we talk about optimizers and backpropagation and all this stuff, I'll bring this up and I'll show you probably some beautiful imagery. But the thing to keep in mind is the neural network really is pretty stupid. Like, it's not actually the smartest thing ever. It's just when you combine all these things, it just can do amazing things. It's like ants or something, right? Like a lot of little basic stuff can do really complicated things. But on this like output layer, we don't really want to have rectified linear because that doesn't really make sense. Instead, what we want is some sort of function that constrains to what we actually want. And what we actually want is only one of these neurons to be fully fired, right? Our goal, like let's say we've got 10 output. I don't really want to write it. But let's say we've got cats, dogs, and humans, right? We want outputs like cat, dog, human, let's say 0, 0, 1. We would want our output layer, if we passed a human, we would want it to say 0, 0, 1, right? That is our goal. These two are off, this one is fully on. But we would also say this would be acceptable, right? So if it was like 78% human and then 0.22 dog. I don't remember what order I said things were. But anyways, we want a distribution like that. So when you're working with something that's like a multi-class, so if it's not a regression algorithm where we're trying to like predict some sort of range. You can do regression with neural networks. That's just not what we're talking about right now. What we're talking about is we've got multiple classes, and what we really want is a probability distribution on the output. So for a probability distribution, we're going to use log softmax. So kind of like when we talk later about our loss, there's different losses that you might use. Optimizer, generally everyone uses the same optimizer like we do with with your hidden layers. Pretty much everybody uses rectified linear. For the optimizer, pretty much everyone uses the same optimizer. But it's when you have different types of what you want as the output, this is where things kind of change. So with multi-class, usually softmax works. So what we're going to do instead is we're going to apply a softmax to this x. So we'll just throw that into our return statement. So we'll return f.log_softmax x. And then we have this other thing that we have to throw in here, which is the dimension on which we want to apply softmax. Now, for an output layer that is of the shape that our output layer is, which will always be flat if we're doing things this way with linear layers, you just assume it's always going to be dim1. But what is this? So dimension equals 1 is, I believe, similar to axes. So if you're coming from like NumPy or pandas, you can kind of think of it like axes. I think. I could be totally mistaken. But dim1 just means it's like which thing is the probability distribution that we want to sum to 1. So in this case, we're going to be passing batches of data. So the output layer will be a batch of tensor distributions. Now, what do we want the probability? What do we want this probability distribution to be a distribution of? I don't know. Anyways, what do we want to sum to 1, basically? It's not all of the batches, right? So like all the batches aren't the probability distribution we care about. We care about the classes themselves. So this will be a batch of tensors. So if we said dim0, we would be like distributing across the batches. So dim1 is we're distributing across the actual output layer, tensors. So anyways, dim1. I probably did a terrible job explaining that, but like I said, you can think of it like an axis, or just say dim1 and don't worry about it, to be honest, because I can't imagine you're going to change that. I don't even know what the default value might be dim1. I really don't know. Anyway, cool. So that's our neural network, and let's go ahead and run that. Make sure. Oops, what? Good thing. That would have been a problem. Let's go ahead and run that. Okay, cool. So it looks like everything sort of works. Let's actually pass some data through the neural network, though. So what we're going to do is, first we need some data. So we're going to say x equals, let's try to mimic an actual image that we might have. So we're going to say capital X equals torch.rand, and then we're going to say it's a 28 by 28. Cool. Let's just look at it real quick. Okay, so man, my nose is super itchy. Okay, so that's pretty meaningless to us, but yeah, those are some random values. Then we could, in theory, pass this to our neural network, but recall, actually, let's pass it. Let's see what happens, because it's, I think it will yell at us. Let's just say output equals net, and then we're literally going to pass x. This is probably going to error. Yes. So we come down here and we see here that we have some sort of size mismatch. Okay, so it says 28 by 28. So, and then the input is a 784. So again, it has to be flattened first. So what is one thing that we could say? Well, we could say x equals x dot view. And then we'll just say 28 times 28. Run that, run this again. And we're like, dude, what the heck? Right? And again, we get some sort of error that if you're new to this, you're going to not understand what the hey this thing is talking about. So instead, what we have to do, and in fact, I don't think I'll get away with this, but let's try this and just pass it. I'm just curious if I get away with it. I don't think I would, but no. So you have to format things exactly how these libraries want them. In this case, we're going to say we actually want to view as a -1, 28 by 28. Let me run that, make sure that works. It sure does. The -1 just specifies that this input will be of an unknown shape. We also should be able to get away with 1 by 28 by 28. We do. And in fact, let me just paste it real quick. Cool. So either way, whether you do -1 or 1, you still get the exact same answer. Why is this? Because this actually is a 1 by 28 by 28. But in theory, this could be many more, right? So you could have a 3 by 28 by 28 or something like that, right? Like, so this will be whatever your batch size is. So we can say -1 because we're basically just saying it's of any size. Just be prepared for any amount of data to be passed through. Don't worry about it. It doesn't matter. And so this just is an array that is of any size, or a tensor rather. But then we just pass it through, and then what is this? These are the actual predictions, right? So this is the prediction for a 0, 1, 2, 3, 4, and so on. It just goes on. Now, there's a couple of things that we didn't quite do. We haven't like initialized weights randomly. We're also like the first few passes of information through your neural network are going to be worthless. Like, they're not actually meaningful in any way. But now you've seen we passed data through the neural network, and we got a return. Now what we have to talk about is what do we do with it, right? So you see gradient or grad fn. That stands for gradient function, and when we pass information through, what we're going to do next is calculate how far off were we. So what was the number that we passed? Who knows? I don't actually know. But we're going to say is the goal, let's say it was a 1, it would be this here. So hopefully this was the argmax. And humans, we think about things in terms of whether or not you were right or wrong. But there's degrees, right? If you're like if you think it's a 1, but you're not really sure, right? That's different than if you're like 100% positive. That's a 1. Well, if it's not a 1, you're way more wrong in the second case than the first case. And that's important if we want to slowly adjust and figure out how we can be right more often. So, cool. So I think that's probably all I really want to talk about up to this point. I don't really think there's anything else that I want to show here. So, quick shout out to my channel members who have been with me now for 6 months, half a year. That's a long time. Howard, Liang, Fidget, Kirill Groshenkov, Cheeky Buns, Frank Lloyd Jr., and Mohammed Almore. Thank you guys very much for your support. It allows me to do what I love to do. So thank you guys very much. Okay. So that's it for now. I feel like there was one more thing I wanted to talk about, and I honestly don't remember. Hopefully I remember at some point. But yeah, there was something really important that I wanted to tell you guys, and it's eating at me because there was something I wanted to say. Can't remember. I remembered what it was. Now I got to edit things. Okay. So this will be way more important like down the line. But one thing to think about is this here, this forward function that we've done, especially if you're coming from any other learning library. You can do fancy things here. So you could say if weather equals sunny, right, or something like that. Do these things at this point. Else, right, do some other things, right? So you can throw logic into this forward method to do whatever you want. So you could actually come up with some really advanced models. And yes, you can do this in other languages. You can branch out and do fancy things, and you can do it, but it's way more challenging. With Pytorch, it's just that simple, and the gradients are automatically calculated, like what you actually ran through and what it needs to adjust. That's really cool. I don't know if we'll actually, I'd love to come up with like a really cool example where we actually do that. One example that I always think about, or at least that I thought about when I figured out you could do that, is like the Python plays Grand Theft Auto. So this is an agent that needs to be able to drive really well, but also do things like if it's on foot, figure out how to steal a car, or maybe do some shooting or something like that. But the primary task of that neural network at first is to just analyze and process imagery. So the first few layers could be image processing layers that are going to be the same whether you're driving or you're on foot or whatever. And then the subsequent layers could be very specific to the task that thing is doing. So think like robotics or other things in general, where the first few layers, that the general task is always the same. And then the next few layers could be very specific to exactly what the task is. So anyway, that was the thing that I meant to bring up and I kept forgetting, and I knew there was something. I knew there was something. Okay, that's it for now. If you can't tell, I'm really excited about that. If you're not excited, then you haven't worked with other libraries, and that is much more challenging. So, okay, see you guys in the next video.